Right, so as I said, the thing we're going to focus on, particularly at the end of this little session where I go through the questions and you've marked it, is this bit where we look at where you particularly lost marks. Okay, so question one. So question one about isotopes. The first part, it says 5 statements that refer to isotopes and some radium isotopes. Okay, so they show us 4 radium isotopes, and we have to identify which of these isotopes it's talking about. And the first one is done for us. So obviously it's the same element, so they all have an atomic number of 88, which means the number of protons is 88. This next one question says isotope with the most number of neutrons. Okay, so Kafasto, how will we work that out?
We take away 88 from the atomic number.
Yes, to get the number of neutrons. Right, so how would you quickly look at this and say which one's going to have the most number of neutrons then?
I'd say the one with the largest number.
The largest which number?
The largest atomic number. So 2 to 26. Atomic mass, yeah.
The largest mass number, yes. So the atomic number is the number of protons. The mass number, the number of protons and neutrons. So the largest mass number will be the one with the most number of neutrons. So that will be this one. Then we have the isotope with the nucleus, which has the largest specific charge. So how will we work that out? What can we say about the charge of these isotopes, the nuclei of these isotopes, Adam? The overall charge for the atom or the overall charge for the nucleus? Yeah, in fact it's both, because the overall charge of the atom is what? What's the overall charge for an atom? 0. So the overall charge for the atom is 0, because we have the same number of electrons as neutrons. Right, so how do we define specific charge, Adam? What is specific charge? Nice and loudly? Yeah, the definition of the specific charge. In relation to its mass, yeah, in relation to its mass. So, in other words, if I want to calculate the specific charge, Edwin, what do I do?
You do charge over mass.
Charge over mass. Okay, right. So, Adam, you said all the nuclei have the same charge. So, which one is going to give us the largest specific charge then?
I'll put the far left one.
The far left one. Yeah, this one. Why?
That's the smallest mass.
It's the smallest mass. Yeah, so it's going to have the largest. It's going to have the largest specific charge. The next one, isotope decays by beta minus decay to form this nucleus, which has got a mass number of 225 and an atomic number of 89. George, what happens in beta decay, beta minus decay, to the atomic number and the mass number?
So as a neutron decays into a proton and an electron, it just adds 1 to the atomic number.
Yes. What happens to the mass number?
It stays the same.
Stays the same. Okay, right. So which one would we pick then?
225.
88. Very good. And then, Darrell, alpha decay. What happens to the mass number and the atomic number in alpha decay?
Mass number increases by 4 and atomic number decreases by 2.
Okay, so which one would we go for then in this case? The second one, because it goes down by 4 and it goes down by 2. Okay, excellent. Right, so now the thing about this question is this could be a multiple choice question. The key thing here is that you're able to answer this question quickly. Yeah, so that's really about practice. It's very straightforward, but it would be, the difficulty is doing it quickly and correctly. Okay, so an atom of one of the radium isotopes is ionized, so now it's got a charge of plus 3.2 by 10 to the minus 19 coulombs. Edwin, what is the value for the elementary charge? And you can use your data sheet if you want to. What's the value for the elementary charge? In other words, the charge on an electron or a proton.
Is it 1.76 times 10 to the 11?
1.76 Se- 76 by 10 to the minus 11. No.
Positive 11.
Positive 11?
Yeah.
Okay, so you would be saying, now let's think about what you said, because this is the charge that's on a proton or an electron, the elementary charge. So that number, 1.76 by 10 to the 11, is that a very large or a very small number?
It's very large.
Is that likely to be the charge of the proton?
No.
No. So this is where it's very important to, when you're in an exam especially, think about, does this seem sensible? So you just said this doesn't seem sensible. So clearly you've picked up the wrong number somewhere. Okay, so you need to go back. Do you have your data sheet in front of you?
Yes.
So look for the charge that's on an electron. What's that? If you start from the top, work your way down. Shall I bounce it, Edwin?
It's the charge over mass ratio.
The charge over mass ratio is the specific charge. We're looking just for the charge. I'm going to bounce it. Faster?
Is it 1.6 times 10 to the negative 14?
It is 1.6 by 10 to the minus 19 coulombs. So the charge is 1.6 by 10 to the minus 19 coulombs. What you were quoting, Edwin, was the charge over mass ratio, the specific charge. Okay. So, but the thing to notice is this is A too large. The other thing to notice is that if you look at that where it's written in your data sheet, it quotes us as coulombs, kilograms to the minus 1. Those are not the units for charge. That's the other reason why in your exams it's really important that you write the units for every quantity that you've got as often as you can. It's going to give you a better chance of getting things right. So this is our answer. Okay, 1.6 by 10 to the minus 19 coulombs. Right, so this is little e is known as the elementary charge. It's the value, magnitude of the charge on the electron or on the proton. Back to you, Kefasto. So how many elementary charges do we say that this ion is going to end up with?
It would have 2 because it's 3.2.
Yes. So this is 3.2 by 10 to the minus 19. That is 2 times 1.6 by 10 to the minus 19. So that is 2 elementary charges. Okay. It's positive. What does that mean that's happened to the electrons? Edwin, back to you. What does that mean for the electrons if we end up with a charge that's positive in an ion?
It lost electrons.
Right, so the positive bit is telling us that it lost electrons, and this bit is telling us how many electrons it lost. So what happens in the process of ionizing this radium atom? It lost 2 electrons. Okay, then we have the specific charge of the ion formed is 8.57 by 10 to the 5 coulombs per kilogram. Deduce which isotope has been ionized. Assume that both the mass of the proton and the mass of the neutron is that value. Now, as with GCSE, the way to do calculation questions remains pretty much the same. You start by writing out what we know. So we've been told that the specific charge, so the E over M ratio, is 8.57 by 10 to the 5 coulombs per kilogram. We know what the charge is because we were told in the previous question that it was plus 3.2 by 10 to the minus 19 coulombs. Okay, so, and we're told, we're trying to work out mass. So we've been told the charge, we've been told the specific charge, and we're trying to work out that should be Q over M. We're trying to work out the mass. So all I need to do is rearrange this equation. So the mass is going to be equal to the charge divided by 8.57 by 10 to the 5, which gives me the mass is equal to 3.2 by 10 to the minus 19 divided by 8.57 by 10 to the power 5. Note that I've written in my units here, that just gives me extra confidence that I'm doing the right thing. Because I'm going to end up with the coulombs are going to cancel. This is divided by kilograms to the minus 1, so I'm going to end up with units of kilograms, which are the correct units. So I'm confident I'm doing the right thing. Okay, and then we put that into our calculator, and we get a value of 3.2 10 to the minus 19 divided by 8.57 by 10 to the 5. That gives us an answer of the mass is equal to 3.73 by 10 to the minus 25 kilograms. It then tells us that we can assume that the mass of a nucleon is 1.66 by 10 to the minus 27 kilograms. Therefore, the number of nucleons is equal to 3.73 10 to the minus 25 divided by 1.66 by 10 to the minus 27. Which gives me an answer of 225. Okay, so now I've written it out very large just so that it's clear on the screen, but it is important that you try and do these calculations so that you're able to logically follow your steps, and that gives us the answer 225. So we've got 225.88 radium is our answer. Okay, question 2. Now the first question, there's often in exams you start with this sort of question, either a straightforward knowledge question, recall question like this, but more often it's actually a definition question. And again, one of the things that you should try and do over Year 12 and Year 13 is build up a glossary of terms that if they said, rather than saying state what is the only stable baryon, what would you have answered if they said state what does a baryon mean? State what is meant by the word baryon. Darrell, what would you say in answer to that? If the question had been state what is meant by a baryon, what would you answer? Those are examples. Yeah, that's true. Those are examples. Bounce along, yeah.
Particles are made of 3 quarks.
Particles that are made up of 3 quarks. Okay. Almost there. Adam, anything else you could add to that? Particle made up of 3 quarks.
Up or down.
The up or down quarks. Okay. Is it only going to be up and down quarks? And strange could be strange. Okay. Anything else, faster you can add?
A subatomic particle made up of 3 quarks that is affected by the weekend straw force.
Okay. Right. Now I'm going to read out what it says in. Well, I'll put it onto the screen. What's said in the textbook. Baryon, a hadron consisting of 3 quarks. So what you said, Darrell, wasn't incorrect. It was examples of what a baryon is. What you said wasn't incorrect, George. You said it consists of 3 quarks. But when you're faced with that sort of question that is really straightforward in an exam, it's really easy to lose lots of time trying to think about how I'm going to formulate an answer. And I would try and build up, with flashcards or just a glossary, a set of definitions for the key terms that you're coming across. Hadron consisting of 3 quarks. So if that question comes up, it's pretty much automatic. You just recall. Yep. Okay. The only stable baryon. What are we going to go for? Proton. Okay. The only stable baryon is the proton. Right. And it then says we've got the aluminium this nucleus of aluminium 2513 decays to magnesium 25, and an electron, neutrino, and another particle are also emitted. So complete the equation to show the changes that occur. Right. It's an electron, neutrino. What are the muons? Oh, sorry, not muons, I beg your pardon. What are the leptons? What leptons do we have? So, Edwin, give me the name of a lepton.
Electron.
Right, so we've got an electron. Darrell, another lepton. A muon, yeah. George, another one. Neutrino, which one? Electron, neutrino. Adam? Muon, neutrino. And is that our lot? Is that all we've got? Faster. Oh, sorry, Adam, go ahead. We have the antineutrinos and the positron and Edwin. No, because that's not a lepton. So we've got an electron, a positron. Yes, Adam? Antimuon. So each of the particles has got the equivalent antimatter particle. Now the reason why I'm saying all this is because it tells us that an electron neutrino is produced. If we have an electron neutrino produced and another particle, is this electron neutrino, is it the matter or antimatter version of the electron neutrino? Which one is it? Is this an antimatter particle or a matter particle? Darrell, what would you say? It's a matter particle, right? Now, it is always produced in conjunction with another lepton. Which lepton is this going to be produced with? That's an electron. It's not an electron. So, a positron. So, write down in big letters, electron always with the anti-electron neutrino, the positron always with the electron neutrino. Because remember, the lepton numbers have to balance. So because this is an electron neutrino means that the other particle must be a positron. Okay, so what are then going to be the numbers? What does the electron or anti-electron, the positron, do to the mass number in beta decay? Nothing. So the mass number is going to stay the same. So that is nothing, and we can see it there. So the numbers match up. And then we've got the aluminium and the magnesium. So what if this was beta minus decay? What would happen to the atomic number if it was an electron being produced? If an electron was produced in beta minus decay, what happens to the atomic number? Yeah. It rises by 1, it does. If this was beta minus decay, it would rise by 1, but it's not. It's beta plus decay, so what happens to the atomic number? It decreases by 1. Okay, it decreases by 1, which means that has to have a value of 1. Now, again, this is something that you want to try to practice. Do it perhaps by writing out these equations lots of times, lots of examples, or write out a little table for yourself that says beta minus, mass number doesn't change, atomic number goes up by 1. Beta plus decay, mass number doesn't change, atomic number goes down by 1. You want this to be recall so that you don't have to really think about it in the exam, it's just automatic. Okay, and then finally we've got name the exchange particle responsible for the decay. Who goes, show of hands, who goes for the gluon? Strong force. Who goes for the photon? And who goes for the weak boson. Okay, and we've got two choices for the weak boson. Who goes for a weak minus? Who goes for weak plus? And who isn't sure? Right, if you're not sure, what should you write down? What would you write down then? You're not sure, you're in an exam. Kivasta, what would you write down?
Just
Try one of them. What would you do, Darrell? You just wrote W boson. Now, interestingly, in the mark scheme, what we see is the answer is a W plus. Condone writing a W boson, but not a W minus, because the W boson means that you might still be correct. The W minus means you're definitely not. Yeah. So, but it is a W boson, a W plus boson, I should say. Okay. Right. Now, next question we have. Helium is the second most abundant element in the universe, and it gives us a long talk about what happened in this heavy ion collider. The first question is one that you must never get wrong. It comes up really often, but you should never get it wrong. Okay, and there are some keywords that you need to have in your answer. Right, so we've got 2 marks. So, George, do you want to kick us off? 1 point that you would write down about isotopes.
You say that the proton number stays, well, the atomic number stays the same.
Okay, so it's the same number of protons, or you could say the same atomic number. That's fine. And Edwin, another point you could make about, oh, but written in the wrong place, I beg your pardon, so let me write it here. The same number of protons, or the same atomic number. And Edwin, another point you could make about isotopes.
The number of neutrons change, so the overall quantity is 0.
If the number of neutrons change, so
The overall charge is 0.
the overall charge is 0. Why would that require a change in the number of neutrons?
Because neutrons have an overall charge of 0.
Okay, but so is before, if I didn't change the number of neutrons, what would the overall charge be?
Still be the same.
Same. So what you're saying is not untrue, but it's irrelevant because the number of neutrons doesn't affect the charge. So it would be unnecessary, but we've got a different number of neutrons is all you need to say, or a different mass number. Right, now that's fine. However, there is one thing else that you need to add. Number, or dropped off there. Yes, Adam. One more thing we need to add. Yes. You must say that isotopes are atoms. Or you can say nuclei with. Always start your answer with. Isotopes are atoms with. Same number of protons, different number of neutrons. This is the main way that people lose the marks on this question. Because you guys now know same number of protons, different mass number. You've known this since GCSE. You're good at writing that. But what people tend to write are things like isotopes are the same element with different numbers of neutrons, right? That's wrong. You need to write isotopes are atoms. Okay, fine. Next one was also a 2-mark question. Explain why 2 photons are formed instead of a single photon when a helium nucleus annihilates with an anti-helium nucleus. Okay? And we're given 2 marks, so we need to have 2 points. Why are 2 photons produced? Fasto.
Is it to conserve energy?
Now, let's think about whether that would be the case. To conserve energy. So it is to do with conservation. Let's think about energy. A photon, how do we define the amount of energy that a photon has? What's the equation? HF. Yeah. You will sometimes see that written like this. Yeah. Okay. But that's just another way of writing h times the frequency. So it's energy is equal to h times f. So I've got a certain amount of energy. It could be carried by 2 photons, half in each photon, or 1 photon. And the 1 photon can still carry that total overall energy. We just have to increase the frequency. Okay? So that's not going to have an impact on energy. Right. So, Edwin, what are we conserving in this case? What are we interested in? What has to happen? What do we want to be conserved? No, we just said energy is not the problem, because energy can still be conserved even with 1 photon by changing the frequency. Darrell, what's going to be conserved? Momentum. Yeah, so momentum must be conserved. So what we've got is we're saying that there is a helium nucleus and helium antinucleus. They collide, right? They're coming together and they collide. So what is the overall momentum before the collision? 0. So the total momentum before the collision is equal to 0. So what will the momentum have to be after the collision? 0. So the total momentum after the collision also has to be 0. If I just had 1 photon, let's travel in that direction, it's going to have some momentum. Okay. So what do I need? I need there to be a second photon, but I need something else about the second photon to make the overall momentum 0. What else can I say about the second photon? It's not just that I need a second one, because here I've got momentum, but it should be total 0. So what can I say about this? Equal energy? Well, it has to be travelling at the same speed, yeah, but what else? So, is momentum conserved if I draw the second one like this?
Same direction.
If it's in the same direction, so both of them going this way?
Opposite direction.
Opposite direction. It needs to be in the opposite direction so that the total momentum is 0. Because remember, momentum is a vector. It has a direction. Okay, so for the total momentum to end up as 0, I need 2 photons traveling in opposite directions. Okay, and those are the 2 points that you need to make. Right, now, this next question is one that tends to catch out a lot of people in exams, because the strange thing here is you need to double and then halve to get the answer. So it says, calculate using data from the passage the maximum frequency of photons produced by the annihilation. So to be able to work this out, we've got frequency, therefore I need to have the energy to be able to work out the frequency. I'm going to somehow have to get the energy. So let's see what information I'm told. In the question, I'm told that the nucleus has got a rest energy of 3728. So I'm going to assume that those are the energies that I'm using. I can ignore the kinetic energy at this stage. So I've got the rest energy before the collision is equal to what? So from the question, I'm told that the rest energy of the nucleus of helium is 3,728 mega electron volts. So what is the rest energy here before the collision? What's it going to be? Is energy and mass, are they vectors or scalar quantities? Is energy vector or scalar? Scalar, okay? So the fact that they're going in opposite directions isn't going to allow them to cancel out. So how would I find the rest energy before the collision? Okay, so what's the rest energy of the helium nucleus, the alpha particle? What's its rest energy? 3728. 3728 mega electron volts is the rest energy of the alpha particle, the helium nucleus. Is that the only particle that we have? How many particles do I have before the collision? Two. Right, so I'm going to have to consider the rest energy of the second particle. What's the rest energy of the anti-helium nucleus?
It's the same as
It's the same, because an antiparticle has got the same rest mass energy as the particle. Right, so this is the first step that you need to do, and it's the step that most people miss out. Right, this is the bit that most people get wrong in this sort of question. You have to start by saying, in any annihilation, I've got two particles, so I need to double the rest mass if I'm given the rest energy for one particle. So that end up with 7,456 mega electron volts. Okay, now I want to work out the frequency. What units do I need for energy if I'm going to use the equation for the photon, the energy of a photon? What units does the energy need to be in? So in other words, this is the equation, E equals h times F. So that gives me F is equal to E divided by h. What units does this energy need to be in to allow me to use this equation? Yes.
Joules.
It needs to be in joules. Yeah.
When I added those two up, I got 6,556 instead of 7,000.
Ah, yeah. Let's see. Have I written down the wrong number there? I think I have. I've transposed my numbers. Yeah. 728 it should be. Beg your pardon. So it's 3,728. I got ahead of myself. I put the numbers into the calculator correctly and I hadn't written them down correctly. That was well spotted. Okay, so I need to convert into joules. So how am I going to do that? How am I going to convert into joules? What do I do? Adam, what do I do to convert from electron volts into joules?
I'm going to try something.
Yeah.
Times it by 1.6 times 10 to the minus 13.
By 10 to the minus 30?
13.
13. And that's when you're converting from what to what?
That's for mega electron volt.
Mega electron volts to joules, yes. So if I'm converting from electron volts to joules, I multiply the energy in electron volts by 1.6 by 10 to the minus 19. Okay? But in your case, you did the one from mega electron volts, so I'd need to multiply by 10 to the minus 13. So that gives me, that's going to be equal to 7456 by 10 to the 6 multiplied by 1.6 by 10 to the minus 19. Which gives me an answer of 1.193 by 10 to the minus 9 joules. Okay, right, now I'm looking for the energy of the photons. What do I need to do now to get the frequency? Sorry, I'm looking for the frequency of photons. What do I need to do now? George, what will be my next step? So what I've done so far, I found the rest energy of the particles before the collision. I had it in mega electron volts, and I've now changed that into joules. And I'm going to be using this equation, E equals hf, to work out the frequency of the proton. So what do I need to do now, George?
I need to do the energy over Planck's constant.
Energy over Planck's constant, right. So put this number in and put energy over Planck's constant. Anybody disagree with that? Okay, now, here is the really tricky bit about these annihilation questions. The next thing you need to do is you go, the energy of a photon is equal to 1.193 by 10 to the minus 9 divided by 2. Because each photon carries half the energy. So that would be 5.96 by 10 to the minus 10 joules. Three significant figures. 965 by 10 to the minus 10, and I'm going to divide that by, therefore the frequency of the photon is equal to 5.965 by 10 to the minus 10 divided by Planck's constant. Somebody can look up Planck's constant for me and shout it out, please.
6.63 times
10 to the minus 34, and that gives me an answer of 9.00 by 10 to the 23 hertz. Now, what is weird about this question? There is something really strange about the way I've done this question. I've done this really long-winded in a way. Right? There's something really strange about it, and what's strange about it is at the start I multiply by 2 to get the total rest energy, and then I convert that into joules, and then I divide it by 2 again before I put it into the equation. And you might say, well, why bother doing that? Why not just take that rest energy, convert it into joules, and use it directly? And here's the reason. In your A level, this question is specifically made so that you demonstrate that you understand what's happening is there has to be conservation of energy, so we have the total energy before, given by the rest mass energy of these two particles, has to be carried away by the two photons. So that multiply by 2 step and then divide by 2 step has to be shown in your workings. Okay, even though it's sort of a step, means that we're doing steps, extra steps in our calculation, you must show that, okay, when you're doing this annihilation question. Okay, any questions about that? Because it's a little bit of a strange calculation in some ways. Any questions about that? Everybody okay with that? Right, okay, so then we're looking at now the complete this equation for the possible decay of an antineutrino. Okay, so we've got a decay process. What type of decay is this going to be? Beta. It's going to be one of the beta decays. Okay. I'm going to work this out just by using the numbers. I've got the atomic number on the left-hand side is 0. So what is going to be the atomic number of this particle that they haven't named? 1, because 1 plus minus 1 is 0. Okay, and what about the mass number? It'll be 0. Okay, so by doing this one just with the numbers, I end up with 0 for the mass number, 1 for the atomic number. There's only one possible particle this can be, which is what? It has to be a beta plus, or I'm doing it this way and a different, just to show a different way of doing the notation, and an anti-electron or a positron. Yeah, I just got that from the numbers. The positron always produced with what? Electron neutrino. Okay, an electron neutrino, not an anti-electron neutrino. Right, then we had what interaction is responsible for this decay? What interaction is responsible for the beta decay? Weak. Okay. Now, next we have the diagram below represents the decay of a particle X into particle Y and 2 other particles. Now, to be honest, doing this question, if I was sitting in an exam doing this question, the first thing I'd do is I'd probably just label these, looking at what the quark composition is. So I've got the particle X has a quark composition of UDD, which means it's what? That's a neutron. And particle Y is 2 U's, 2 ups and a down, so that's a proton. Okay. So that probably would have been the first thing I would have done just looking at this question, just sketch those in. So then, the quark structure of the particles are shown. Deduce the name of particle X. We've already done that. It's UDD, so that means it's a neutron. And it says the name, so I have to put in the name. Okay, what's the type of interaction that occurs in this decay? It's shown in the Feynman diagram. Adam, what type of interaction is it? Weak, so we see it directly from the Feynman diagram. We've got a W minus boson. What's the class of particles to which the W minus belongs? Edwin?
Boson.
It's a boson. You can also say exchange particle. You can say that, but boson is the easiest and the best thing to say. Show clearly how the charge and baryon number are conserved in this interaction. You should include reference to all the particles, including the quarks. Right, now, the key thing about this question is it says show, and show means that you have to show all your workings, right? So that means that you need to show what's happening on the charge. Okay, so what I have is I've got UDD goes to a UDU plus an electron, an electron plus an anti-electron neutrino. Okay, so I'm going to look at charge. It says including the quarks, so I need to show the charge of what in this question. What do they want me to show? What does the examiner want me to show them? So when I say the question, if I say show the charge of all the particles including the quarks. Yeah. Show the charge of the quarks. Right? Now, when I say it like that, when I take out these words and I go show charge all particles including quarks, it becomes very much easier to understand what they're looking for, I think. So what we're going to have to show is we're going to have to show the charges of the quarks. So this is all given in our data sheet. We don't have to remember it. The charge on the up quark is, somebody shout it out, 2/3, and these are all times E. Okay, the elementary charge. And the down is a charge of minus 1/3, so that's going to be minus 1/3. Okay, and that all has to be equal to what? That's all equal to 0, but that always has to be equal to what's on the other side. So on the other side I've got, for this one, 2/3, the down is -1/3 plus 2/3, and the electron is -1, and the neutrino is 0. And I could write true, so charge conserved. Okay, and I can say then the same for the baryon. Okay, so for the baryon number of an up quark is, what's the baryon number of an up quark? 1/3. And for the down, 1/3 as well. Okay, and that has to equal 1/3 plus 1/3 plus 1/3. What's the baryon number for the electron? Sorry, Adam? 0. And for the anti-electron neutrino, 0. Okay, true. So the baryon number is conserved. But the important thing is that you've shown the charge for all particles, you've shown the baryon number for all particles. That's what gets you the marks. Okay? Right. So that's that question. Anyone that didn't get that question right is probably down to really reading the question. Is really what's tricky there. Only stable baryon, once again. Proton, yeah. A muon is an unstable particle. State the names of the particles that are produced when a muon decays. So what is produced when a muon decays? Electrons, yeah, that's one. We get an electron, yeah. And if we get an electron, then what do we always get with it? Electron, antineutrino. Okay, and anything else? Is that it? A muon neutrino. Okay, if we look back, when you do the Feynman diagram, so you have this interaction. Let me see, it's probably already drawn. The muon goes to, and we have electron and an anti-electron neutrino. Okay, so this is the Feynman diagram for the muon decay. If I didn't have this, if I had just written down an electron and an antineutrino, I'm not going to get this to balance, because I've got a lepton number of 1 coming in, and especially if I do make it a muon lepton number of 1 coming in, and on this side my muon lepton number is 0. So I need to have this balance, so I needed to have a muon lepton number of 1 coming out. What is the boson in this case for this interaction? Which one? What's the charge coming in? Negative. What's the charge on this muon neutrino? What's the charge on a neutrino? 0. So I've got negative 1 coming in, 0 coming out here, so what do I need here? I need positives. Remember, this is the before, and this is the after, and these have to be the same in terms of the charge. So here I've got a charge of -1 coming in before, so overall afterwards I need what charge? -1. So what boson will I have here? W minus. W minus. Yeah. It's very important that you think about what's happening before and what's happening after the interaction. So this interaction is shown as the muon is going to decay to give me a muon neutrino plus an electron plus an electron antineutrino, like that. Okay, make sure that you've, I'll just leave that there for a moment so that you have a chance to see it. Make sure that you've spent a little bit of time going back through those interactions so that you're confident that you can identify the decay process, the particles that are produced, and the boson that's involved in any of these decay processes. Okay. Right. Everybody okay with that? No. By the way, one last thing on this question, so that I've really done it to death. It says state the names. So if I had written down this, if I put down this as the answer, that is correct, an electron plus an electron antineutrino plus a muon neutrino, that's correct, I would get nothing for that, because it says state the names. Okay. Right. Now, question 5. We have complete the table comparing some of the properties of the positive pion and the proton. So we're looking for the relative charge. So we have charge of the pion +1. It's relative charge, so we can just write that as +1. The baryon number, the pion has got a baryon number of 0. What type of particle is this? It's a meson, yeah, and the mesons have a baryon number of 0. The proton has got a baryon number of 1. And quark composition of the proton is up, up, down, and for the pion plus up and anti-down. Okay. Now, when a positive pion interacts with a proton, a kaon is produced, along with another strange particle as shown in the interaction. Okay. So here we are producing a kaon. The interaction, when we produce kaons, is what? What boson is involved when we produce kaons? Who goes for the strong interaction? Who goes for the weak interaction? Who goes for the electromagnetic interaction? So the answer is strong. We've only got quarks involved here, and we're producing a kaon. When a kaon decays, we have the weak interaction because it's going to produce leptons. But when it's the kaon being produced, it's the strong nuclear. Okay, next we have to deduce the relative charge, the baryon number, and the strangeness number of the particle X. So I'm going to just write this down, plus the proton to give me the kaon plus X, and I've got charge, I've got the baryon number, and I've got the strangeness number. Okay. The charge on the pi plus is the pion, positive pion. Edwin, what's the charge on the positive pion? +1. What's the charge on the photon? Yeah, proton, I should say, +1. And what's then the charge on the positive kaon? +1. So that means plus X, therefore the charge on X is +1. Right, the baryon number of the positive pion capacitor, 0 on the proton. The baryon number on the kaon, so that means that the baryon number has to be 1. Okay, and then we've got the strange number for the positive pion atom, and for the proton, for the positive kaon, +1. So that means that the strangeness of X equals -1. Okay. Particle X can decay to produce a neutron and a positive pion as shown in the equation. Here we've got a decay process. Okay. Which type of interaction will this be? Which type of interaction? What are we going to go for? Okay, is it, who would go for this? We've got essentially 4 choices. Who goes for gravitation? Who goes for electromagnetic? Okay, so we know it's not either of these two. We're always in between these two. Right. This we've already worked out. Its charge is +1. Its baryon number is 1. Its strangeness number is -1. Okay. Let's think about then what's going to happen in this decay process. Is charge being conserved? First of all. Yes, it is. I've got +1 on this side, I've got 0 and +1 on that side, that's fine. Is the baryon number being conserved? The baryon number of the X is 1, the baryon number of the neutron, and the baryon number of the positive pion. So is the baryon number conserved? Is the strangeness number conserved? No. Right. Strangeness isn't conserved. What is the rule about the conservation of strangeness? Yes.
Strangeness is only conserved with strong interaction.
Yeah, and the other way you could say this is strangeness. So I can say is not conserved. And I'm going to say strangeness is always conserved in strong interactions. Okay? The strangeness is not conserved. If it was the strong interaction, it would be conserved. So which boson is involved here? Weak. So that leaves me with the weak. So it's a process of elimination. So again, this is about being really familiar with your conservation rules. Really being so familiar that it becomes automatic. Strangeness isn't conserved, therefore it can't be strong, therefore it must be weak. Thank you. Right, and then we had explain your answer. Well, the answer is the strangeness is changes. There's 2 marks, so you could say the strangeness is not conserved because X has strange of +1, but the neutron and ion plus, -1, pardon, thank you, -1, but both have strangeness of 0. Okay, and then we say this means it can only be the weak interaction. Okay, so that's just putting in words the process we went through. Strangeness is not conserved because it went from -1 to 0, therefore it must be the weak interaction. So again, and maybe this is what I was trying to get at when I was speaking to you right at the start of the lesson about if you want to move away from the sea, what's involved. It's more than just doing what we're homeworks and things that we're telling you to do. It's really you need to be completely familiar with those conservation rules so that it becomes automatic when you're doing this sort of question. Yeah, and that can only happen by you putting in a lot of legwork, doing a lot of reading back through it, answering questions, making sure that you know these things completely. Okay, it then says the neutron and positive pion will then decay. The positive pion can decay into a positron and an electron neutrino. Write down the equation for the decay of the neutron. Okay, this question, do I need to know anything more about the decay of the positive pion to answer this question? No, so if you did put anything down about the positive pion, then automatically that's going to be wrong. So I've got a neutron, it's a decay, so that's going to give me something. What is the neutron decay into? Proton, the only stable baryon, plus it's an electron and an electron antineutrino. Okay. Beta minus or electron and the antineutrino. Explain why no further decays are possible. Why are there no further decays possible? Yes. Right, so because the proton is the only stable baryon, literally stealing the words from that question to answer this one. The proton is the only stable baryon. Okay, so that one's okay. What about the electron and the electron antineutrino? What can I say about that? Okay, so
Do you remember how much the lab looks like?
250, I believe. Yeah.
That was the charge you.
Then
Let's stick to that then.
then let's stick to that then. Yeah. Yeah, yes, but no. Because here's why. How would you describe the muon? Is the muon a fundamental particle? Yes. Does it decay? It does not. Well, let's just think back to the questions that we've been answering, because where did we have it? We had it there. A muon is an unstable particle. State the names of the particles that are produced when a muon decays. So, and I know that a lot of you wrote this down. You said that an electron and an electron antineutrino are fundamental particles, therefore they can't decay. That's not true. Fundamental particles can decay. So the only thing you can say is that the electron and the electron antineutrino are stable particles. That's all you can say. That was one of those questions that I think is designed to try and trick you. It's trying to get you to say what you just said, Edwin, that it's a fundamental particle, because that's wrong. Because fundamental particles can decay. Okay? Right. Two baryons. Darryl, since you said this earlier in the lesson, two baryons. Proton and neutron. Yeah. Proton and neutron. And again, it says name, so I have to write out the names. State the quark structure of the positive pion, that is positive pion. Up and anti-down. Yeah. The kaon plus is a strange particle. Give one characteristic of a strange particle that makes it different from a particle that is not strange. Yes. It has a strange quark in it. That's the easiest answer to give. I agree. Now I'm just going to zoom in on the mark scheme to show what they said, what was possible. But by far the easiest answer to give there is that it contains a strange quark. Decays by the weak interaction, longer half-life than expected. Those are characteristics of why it's called strange. It's called strange because it has a longer half-life than it's expected for that type of particle. But by far the easiest thing to say is it contains a strange quark. Okay, and I'm going to go back here. I'll put that in as one characteristic. It contains strange quark. One of the following equations represents a possible decay of the K plus kaon. State with a reason why one of these decay processes is not possible. So, what is this question about? What are we going to be using? George, what are you going to be using to answer this question? What is this question about?
So we'll be using the conservation rules.
It's about the conservation rules. So what we really need to say is, which one of these breaks one of the conservation rules? So let's just go through this in order. So we'll start with charge. So let's work out the charge. So if I start with equation 1, what have I got on the left-hand side for charge? Plus 1, and that has to be equal to, on the right-hand side, plus 1 and 0. So that one's okay. What about this one? Plus 1 equals plus 1 and 0. So that one's okay. Right, let's try the baryon number. Darryl, if you go through those ones, for the baryon number conservation, for the first equation, what have I got on the left-hand side? So I've got a baryon number of 0 has to be equal to 0 plus 0, so that's okay. And then for this one, equals plus 0, okay. And then I've got the lepton number. Okay, and for Edwin, for the top equation, looking at the lepton numbers, what's the lepton number for the positive kaon? 0. And that is equal to, on the right-hand side, lepton numbers. For the positive Positive pion at the top. What's its lepton number? Okay, so what is the positive pion made from? It's written here. Up and anti-down. Are those leptons? No. So what's its lepton number going to be then? 0. Very good. So that's 0. And what about then the other meson, the pion, the neutral pion? It's also a meson, which is a quark and an antiquark. So its lepton number is going to be 0. So that one's fine. And then we'll look at the second one. So looking at the second one, I've got 0 is equal to, so Edwin, if you finish it off for us, we've got then the anti-muon, what's its lepton number? -1. And I've got a muon anti-neutrino. It's got -1 as well. So is the lepton number conserved? No. Okay. So which decay is not possible? The second decay is not possible because the lepton number is not conserved. Again, once you do lots of this will become really, really fast. You won't have to write it out. Say the charge and the bearing, you can probably do that in your head very, very quickly. But it's useful just to do these things. Get used to doing them systematically, just at least to start off with. Okay. And then the next part of this question, another strange particle. X decays in the following way. We've got a particle decaying to give me a negative pion and a proton. It's a decay process. Which interaction are we going to go for? So who's going to go for, we're only going to be deciding between strong and weak, obviously. Who's going to go for strong? Who's going to go for weak? Yes, it's weak. So this is going to be the weak interaction. Show that X is a neutral particle. So this is a show question. Okay? So what do you need? What means that X must be neutral? How are we going to get that? George.
So as it's pi minus, that means it's equal to, it has a charge of -1.
Yes.
And the proton has a charge of +1.
Okay.
That means the overall charge on the right is 0.
Yes.
On the left has to be 0 as well.
Yes, it has to be 0 because?
Because the charge is conserved.
Okay, so I'm going to start my answer by saying charge must be conserved. The overall charge of the products is -1 + 1, which is equal to 0. Therefore, the charge on X is 0. It's really important in this question that you say that charge must be conserved. Yep, you have to write that in. Even though the examiner will know that, you have to assume that they won't in order to answer that. Deduce whether X is a meson, a barium, or a lepton, explaining how you arrived at your answer. Okay, so what are we going to use here to figure this out? Yes?
The concentration is barium number.
Right, okay, so what did you decide then that X was?
I decided it was a barium because the proton has a barium number of 1. So it's X must have 1 as well.
Okay. Barium number is conserved. So the barium number of the products, again, just repeat to me what you said, Adam, about the barium numbers of the products.
Well, the proton has a barium number of 1.
Yes.
So X is barium number 1.
What's the barium number of the negative pion? 0. So overall, it's got a barium number of 1. Therefore, X must have a barium number of 1. Okay, very good. And which particle in this interaction is the most stable? Once again, same question, and that is proton. Okay, and on to the last question. So in another of these tables to fill in, and this is the sort of thing that you want to be able to do quickly. So I've got to fill in particle name, I've got the quark structure, the charge, the strangeness, and the baryon number. So the top one, what is it? It's a proton. It's an up, up, down. Its charge is +1. Its baryon number is +1 or 1. The sigma plus particle, it's an up, and a strange. So its charge number is +1. Its strangeness number is -1, and its baryon number is 1. And then I've got the last particle, which is an up and an anti-down, so that is pion plus, positive pion. Its charge is +1. Okay, excellent. So each of the particles has an antiparticle. Give one example of a baryon particle and its corresponding antiparticle. What will we go for? Proton and an antiproton. Okay, fine. State the quark structure of an anti-baryon.
Would be 3 Qs per diameter.
Okay, or how could you say that in words?
3
3 antiquarks. So they just 3 antiquarks. Yep. One thing that I think some people did things like they wrote down something like that. Right. That's a particular particle. This asks generally what is the quark structure of an antibaryon, so it has to be 3 antiquarks. And then finally, give one property of an antiparticle that is the same for its corresponding particle and one property that's different. Edwin, a property that's the same.
Mass is both unstable.
Yeah, so we've got the same mass energy. Yeah, and I'm going to write that. And then the one that's different, Darrell, charge. Yeah. Okay, very good. Right.